Crater Lake in southern Oregon is the deepest lake in America. Almost 2,000 feet of water, so clear you can see down over 100 feet. What 500,000 tourists are standing on when they visit the rim is a volcanic crater called a caldera, one of the most dangerous volcanoes in the country. Southern Oregon, 2011. For the first time in history, a volcano science team installs earthquake sensors inside the Crater Lake caldera. 3 stations along the rim and a 4th on Wizard Island, the volcanic cone jutting out of the water near the western shore. The lake sits in one of the most remote national parks in the lower 48 states, buried under snow for most of the year and reachable by road only in summer. Before this, there is no equipment set up to listen to what is happening beneath the deepest lake in America. Nothing. The nearest instruments sit outside the park, kilometers away, built to track earthquake activity across the Cascades, not the specific rumblings of a single volcanic crater. A volcano ranked in the top 18 most dangerous in the United States. And for decades, nobody has instruments close enough to hear it. This decision seemed small at the time. It wasn't. It takes less than 2 years for the network to pick something up. On October 25th, 2013, 3 small volcanic earthquakes show up on the stations. The largest is roughly magnitude 0.8, tiny, barely a whisper. These are not surface quakes caused by shifting plates. They are volcanic earthquakes, created by stress changes in rock near a magma source. The kind of event that would go completely unnoticed without equipment built just for this purpose. The official announcement describes these as the first earthquakes recorded at Crater Lake by the new monitoring network. That wording, by the new monitoring network, is doing critical work. It means these are the first quakes picked up by the new equipment, not the first quakes ever. Earthquakes near Crater Lake have been recorded since at least 1920, when a roughly magnitude 4 event shook the area. In 1947, a magnitude 3.7 quake struck near Fort Klamath, south of the park. In 1994, 3 quakes between magnitude 2.3 and 2.6 rattled Rim Village, the main visitor area, years before any earthquake sensor sat inside the caldera walls. That difference gets stripped when the headline travels online. First earthquakes ever under the water is what spreads. The wording disappears. So does the date. And the context goes with it. And from there, the story twists into something the science never supported, recycled year after year as if it is breaking news. But the clickbait is not the interesting part of this story. What the instruments actually find beneath that water is. Crater Lake sits at 6,178 feet above sea level in the Cascade Range. The lake fills a caldera roughly 8 by 10 kilometers wide and holds nearly 5 trillion gallons of water. There is no river feeding it, no stream running in or out. Every drop comes from rain and snowmelt, and the lake loses water only through evaporation and slow seepage through volcanic rock. The entire volume replaces itself roughly every 250 years. It is a closed system, sealed by the very geology that created it. The water is cold. Near the surface, temperatures sit around 50 degrees Fahrenheit in summer. Near the bottom, just above freezing, the clarity is staggering. It is measured by lowering a black and white disc called a Secchi disc into the water until it vanishes from sight. The long-term average depth where it disappears is nearly 100 feet. The record is 142 feet, set in 1997. That clarity exists because there is almost nothing living in the upper water to cloud it, which makes what sits at the bottom even harder to explain. In 1988, a small one-person submarine called Deep Rover is lowered to the bottom of Crater Lake. It is the first time anyone has seen the caldera floor with their own eyes. The deepest freshwater setting in the country, sitting in near total darkness under crushing pressure. The expectation is cold, bare, lifeless rock. What they find is the opposite. At nearly 2,000 feet down, in water that should be completely freezing and lifeless, there are hot water vents. Warm, mineral-rich fluid seeps upward through cracks in the volcanic rock of the caldera floor. Bacterial mats, thick clusters of tiny organisms feeding on sulfur and iron, spread across the lake bottom near these outflows, powered not by sunlight but by chemical energy from beneath the Earth's crust. In the south-central basin, there are pools of shimmering water sitting in dips on the floor, warmer and saltier than the lake above them, with visible edges where the pool water meets the surrounding lake water. Fluids loaded with carbon dioxide, iron, manganese, and sulfur collect in these dips. One of the largest is known as Lau's Bath. Near Palisades Point in the Northeast Basin, more warm pools cluster in another active zone. Standing among these vents and pools are mineral towers built by the slow buildup of dissolved minerals from the vent fluid. Some reach over 30 feet tall. They look like chimneys built by a process that is still going on. This is not what you find at the bottom of an untouched mountain lake in Oregon. This is what you find at the bottom of an ocean, near a mid-ocean ridge where the Earth's crust is pulling apart. The heat driving these vents is active energy from the same magma system that built and then destroyed the mountain this lake replaced. Research at these vent sites has continued for over 3 decades. More recent work has found unexpected variety in the bacterial mats, finding communities far more complex than anyone predicted. The organisms are not just surviving. They are building a living system powered entirely by volcanic chemistry. The vents are not shutting down. They are keeping life going. Pay attention to this next detail, because it explains everything about why Crater Lake exists. Roughly 7,700 years ago, a towering volcano called Mount Mazama stands where the lake is now. Its summit reaches roughly 12,000 feet. It has been building itself through eruptions for over 400,000 years, stacking flows of volcanic rock one on top of another. The Klamath people, whose homeland includes this region, carry a spoken history describing a world-ending battle between sky and underworld spirits that results in the destruction of the mountain, a story now understood to be a remarkably accurate eyewitness account passed down through roughly 300 generations. Then Mazama erupts in a way that dwarfs almost anything in the geological record of the past 10,000 years. Roughly 50 cubic kilometers of magma, about 50 times the volume that Mount St. Helens threw out in 1980, blasts out in a single devastating event, rated 7 on the Volcanic Explosivity Index. Pyroclastic flows, superheated walls of gas and rock, race outward from the collapsing summit and travel up to 70 kilometers down every drainage. Ash rains across 8 American states and 3 Canadian provinces. The eruption column punches into the upper atmosphere, and the resulting ash layer is so widespread that scientists across the Pacific Northwest still use it as a time marker in layers of soil. If you dig into the ground anywhere from southern British Columbia to northern Nevada and find a pale gray band of volcanic ash, there is a good chance you are looking at Mount Mazama. And then the mountain collapses. Without the magma holding it up, the summit caves inward, dropping thousands of feet into the void. What remains is a caldera, roughly 8 by 10 kilometers across and over 1,000 meters deep. Over the next few centuries, rain and snowmelt slowly fill the bowl. No rivers, no streams. Just rain and snow building up year after year until the water reaches a steady level. That process is still happening. The same magma chamber that powered Mazama's destruction still sits beneath the caldera floor. It is cooler now. It is not making the kind of magma that could fuel another massive eruption, at least not on any timeline that matters to humans. But it is still there. The hot water vents prove it. So do the warm pools. And the bacterial mats feeding on volcanic chemistry nearly 2,000 feet underwater leave no room for doubt. And the earthquakes prove it too. After that first detection in October 2013, more seismic events follow. In April 2014, roughly 20 volcanic earthquakes show up on the network at depths of 5 to 10 kilometers. In May 2015, 4 more. Then, in June 2020, a magnitude 1.3 earthquake strikes directly beneath the lake itself, near Dutton Cliff on the southeast rim, at roughly 2 kilometers below sea level. 24 aftershocks follow over the next 12 hours. This is the first time the network records a clearly located earthquake beneath the water surface of the lake. The official assessment of this activity is that it is more or less normal for the volcano. That's not a typo, by the way. More or less normal. Because while the earthquakes are small and consistent with background volcanic activity, the network picking them up has only 4 stations. 4. For a caldera, 8 kilometers wide, holding 5 trillion gallons of water, ranked the 17th most dangerous volcano in the entire United States. Compare that to what sits on other Cascade volcanoes at the same threat level. Mount St. Helens, ranked number 2, has dozens of earthquake stations backed up by ground shift monitoring, gas detection equipment, and a fully staffed watch center with direct line of sight to the crater. Mount Rainier, ranked number 3, has tilt sensors, real-time ground shift monitors, and mud flow detection systems wired into warning sirens in downstream communities. Mount Hood, ranked number 6, sits under constant multi-tool watch because it sits close to the Portland metro area. Crater Lake, ranked number 17, 4 earthquake sensors. One of them on a volcanic island in the middle of the lake. No permanent instruments on the lake bottom, where the hot water vents and the most recent volcanic activity are centered. No tilt sensors, no ongoing gas tracking. The equipment is so thin that when an earthquake occurs beneath the water, the network can tell that something happened, but often cannot pinpoint exactly where. The location error is too large with so few stations. This gap between threat ranking and monitoring spending is the actual story, not the clickbait headlines, not the recycled 2013 press release being passed around as if it dropped yesterday. The real concern is that Crater Lake is a confirmed active volcanic system, sitting beneath nearly 5 trillion gallons of water, with barely enough equipment to tell you something moved. If you're finding this useful, subscribe. We cover stories like this every week. The Caldera floor holds the remains of at least 3 eruptions that happened after the mountain collapsed. Wizard Island is the one everyone sees. A cinder cone rising 755 feet above the lake surface, topped by a small crater called the Witch's Cauldron. Hikers can take a boat to the island in summer and walk up to the rim of a volcanic crater that formed while the lake was still filling around it. The island covers about 316 acres. Merriam Cone is the one nobody sees. It sits entirely underwater in the northeast part of the lake, rising roughly 1,400 feet above the caldera floor. Its summit is still 505 feet below the surface. It has a smooth top with no crater, physical proof that it erupted beneath the lake. The weight of the water above held back the explosive gas release that would normally build a crater. Instead, lava piled up in a mound. And then there is a third feature, less talked about than either cone. A small dome of volcanic lava sits on the east side of Wizard Island, completely underwater, found only through underwater sound mapping. It marks the last known eruption at Crater Lake, roughly 4,800 years ago, the most recent proof of magma reaching the surface inside the caldera. And it formed underwater. 3 eruptions after the collapse, all of them within the caldera, 2 of them entirely beneath the surface. The pattern is clear. When Crater Lake's volcanic system produces its next eruption, it is most likely going to happen beneath the water. You'd think someone would have said something about the monitoring gap sooner. Nobody did. At least, not loudly enough to change the funding. Between 500,000 and 750,000 people visit Crater Lake National Park each year. Many of them drive up to Rim Village, park their cars, and walk to the edge to take photographs. The elevation at the rim ranges from 7,000 to 8,000 feet. The parking area sits within half a mile of a major fault zone. Almost none of the visitors know any of this. The primary hazard report for the caldera, still the go-to document nearly 3 decades after it was written, outlines what a future eruption looks like. The most likely events are small to medium eruptions in the western half of the caldera, beneath the lake's surface. If rising magma reaches shallow depths and meets the water, the result is a steam explosion, a violent blast that can throw rocks beyond the caldera rim and send pyroclastic surges, fast-moving clouds of superheated gas and debris, across the water surface and onto nearby land. The caldera walls pose a separate risk. They are steep, badly worn, and in places weak and crumbling. An eruption could trigger landslides into the lake, sending waves that would race across the surface. But the rim stands over 150 meters above the water, at its lowest point. The water stays in the bowl. Volcanic debris, the mix of ash and rock thrown out during an eruption, would fall across the surrounding landscape. Depending on wind direction and eruption strength, communities within tens of kilometers could see noticeable ashfall. And there is an added earthquake risk that has nothing to do with the volcano itself. The West Klamath Lake Fault Zone, a crack in the earth unrelated to the magma system, runs within half a mile of Rim Village and is able to produce earthquakes up to roughly magnitude 7. Its repeat cycle is estimated at every 3,000 to 10,000 years, which sounds distant until you consider that the last major event on this fault has not been precisely dated. A repeat of the original Mazama eruption, the devastating level 7 event that created the caldera, is considered very unlikely. The right type of magma needed for that kind of eruption does not appear to be present beneath the caldera today. What is present is a cooling but still active hot water system, occasional small earthquakes, and a volcanic history that includes at least 3 eruptions inside the caldera since it formed. The system is not gone. It is sleeping. The current alert level is normal. The aviation color code is green. There is no earthquake swarm, no ground shifting, no change in gas output. As of May 2026, roughly 23 small earthquakes have been recorded within 30 kilometers of the caldera since 2023, none larger than magnitude 1.8. This is background noise for an active volcanic system, and it is well within the range of what scientists expect. The real question is not whether Crater Lake is about to erupt. It almost certainly is not. The real question is what happens when the background noise changes. When the earthquake rate jumps from a handful per year to dozens per week. When the vent output shifts in temperature or chemistry. When the caldera floor starts tilting or bulging. The instruments that would catch those signals early, that would give scientists weeks or months of lead time instead of hours, mostly do not exist at Crater Lake. 4 earthquake sensors cannot do what a full monitoring network does. At well-watched volcanoes, the buildup from background to eruption follows a clear pattern. Earthquake swarms pick up, the ground shifts. Volcanic gases spike. At Mount St. Helens before the 2004 eruption, weeks of rising earthquake activity gave volcano scientists enough warning to close the area and raise the alert level through multiple stages. Nobody was caught off guard. The monitoring worked. At Crater Lake, if a similar buildup began beneath the lake, the 4 stations would pick up rising earthquake counts, but exact locations and movement patterns would stay fuzzy. Ground shifts would go unnoticed. Gas changes beneath the water would go unmeasured. The warning window that other Cascade volcanoes would provide might, at Crater Lake, shrink to almost nothing. And the gap between what we know about this caldera and what we are set up to detect in real time is the part of this story that no viral headline is covering. The deepest lake in America is still the bluest thing most visitors have ever seen. The water is still impossibly clear. The rim trail still draws 500,000 people a year to stand on the edge and look down. The question nobody is asking is whether we would know in time if something beneath all that blue started to change.